Welcome to this tutorial on the AASHTO Strength design checks within Embrace 3D. These capabilities were introduced in version 4.0 of the software. The idea of this video is for you to get an understanding of the different strength design checks currently covered within the program, how Embrace 3D performs these checks, and illustrate these capabilities on the AISC and SVA design example 4. The idea to be able to run these checks is to have one model for DC1S, another one for DC1C, DC12, DW, and LL plus IM. For those who are not too familiar with this terminology, DC1S refers to the effects of the steel superstructure only. DC1C refers to the effects of the wet concrete load on the bridge. DC2 refers to the effects of the barrier line loads on the long-term composite section. DW is very similar but refers to the effects of the wearing surface, and LL plus IM refers to the effects of the live load on the short-term composite action, really, including the dynamic load allowance. Of course, for LL plus IM, you need to run an influence surface analysis. This is very important. The bending moment, which is required for the design checks, is obtained by computing the position of the elastic neutral axis on the section and then integrating the longitudinal stresses with respect to that axis. The principal bending stresses, F sub B, are obtained by dividing the moment by the appropriate section modulus. And for the lateral bending stresses, we are subtracting the longitudinal stress at the flange center node from the stress at the flange tip. The same applies to the resultant shear force. It is obtained by integration, by integrating the vertical shear stresses over the section. Here are the checks performed by the program. Because we are looking at horizontally curved sections, we are looking at chapter 6.10.7.2. We are looking at these checks on the compression flange, this one on the tension flange, which includes the lateral bending stress, and we're also limiting the lateral bending stress with equation 6.10.1.6-1. For negative bending, we are looking at chapter 6.10.8. We have this classic equation, which we need to conduct both for FLB, flange local buckling, and LTB, lateral torsional buckling. There is also an additional check on the top flange, which is in tension for negative bending. Note that the hybrid factor R sub H is calculated automatically in case the flanges and the web have different grades of steel. The web load shedding factor R sub B is also calculated automatically, but maybe more importantly, the unbraced length L sub B, which is required for the LTB checks, is also calculated automatically based on the cross-frame arrangement that the user has implemented within the model. So that would cover both X frames and K frames. A moment gradient factor C sub B of 1 is assumed, which is conservative, but if you open the Excel spreadsheets for the design check, you are welcome to increase that number if necessary. For the shear resistance, there is an option in the program, we will see that in a minute, to have additional user-defined transverse web stiffeners for design checks. These stiffeners will not be explicitly modeled in the finite element mesh, but they will play a major role in increasing the shear strength of the panel, of course. Additionally, the program will recognize whether we are looking at an end panel or an interior panel. So to illustrate these capabilities that have been released in version 4.0, the latest one at the time this video is being recorded, We're going to look at design example 4, and we're going to look at 3 different limit states. So there are really 3 spans here. The first limit state will be positive bending at midspan of the third span here for girder 4. Limit state number 2 will be negative bending at pier number 2 for the exterior girder again, which is the critical girder. And the third and final limit state will be the shear at the end abutment. Here are the results for some of the influence surfaces. So for the first limit state, this is the critical vehicle loading for positive bending at midspan of span number 3. This will be the critical loading for negative bending at pier number 2, okay, and we can clearly see here the dual truck, okay, there are 2 trucks per lane, which is really important. We are really following AASHTO here. And then for shear, this would be the corresponding influence surface. The values here reported are also compared to the published value in the AISC design guides. So here now we're going to go over really the spreadsheets that are then produced by Embrace 3D. In a first step, the program will compute the composite section properties. So first we're going to look at positive bending. So the first step is to look at these composite section properties, extract the bending moments and the lateral bending stresses from the FEA model for the different models, okay, DC1S, DC1C, etc. Compute the principal bending stresses, including the load combination factors from the strength 1 design combination from AASHTO. And finally, verify the strength design equations from the 10th edition of the AASHTO LRFD bridge design specifications. For negative bending, the workflow is very similar. We first compute the composite section properties with or without the longitudinal steel reinforcement. We extract the bending moments and the lateral bending stresses from the FEA model. And we compute the principal bending stresses, which will be used for the strength design checks. And here they are. Here are the strength checks for negative bending, including FLB, flange local buckling, LTB, lateral torsional buckling, with an additional check on the tension flange for yielding. Finally, for shear, we extract the shear forces from the FEA models. Again, there are 5 models to look at, and we calculate the shear strength and verify the strength design equation. Apologies if this is slightly cut here. This shows a value of 0.31, which is not needed as we're looking at the end panel, we're looking at the abutment, so the 0.58 value controls. A summary of the design checks is provided automatically in the program. So we can see here these values. A value in red will mean that it's above 1. In orange, it would mean that it's between 0.9 and 1. And if it's less than 0.9, it will be shown in green. There is also the option to click this Excel button, which will automatically open the spreadsheets corresponding to all these design checks. And we're going to look at this in a minute. So to conclude, and I'm not going to read all of these because this presentation is available on the website. You now have the ability in version 4.0 to look at the bending and shear strength design checks in full compliance with the 10th edition of the AASHTO LRFD bridge design specifications for curved steel bridges, for curved plate girder bridges. This is done on a refined 3D shell models, which is really the state-of-the-art methodology for curved bridges or potentially even skewed bridges. You do not need any distribution factors. This is all taken care of by the finite element model. You need at least 5 models, possibly 6 if you look at negative bending and maybe the dual truck model for LL plus IM. You are able to model longitudinal deck reinforcement for accurate calculations. There is an option to have additional transverse web stiffeners for shear strength design checks. So all of this is a massive improvement in the software, going beyond analysis and now including design checks. You can verify all of these calculations in Excel if necessary. This is fully transparent, and you can include these calculations in calculation reports for your client to document your design. And this is, of course, the reference document. Now let's look at the model in action. So first of all, you will need to specify steel grades for the 4 girders. Here I have a grade of 50 KSI steel for all plates, including flanges and webs. As mentioned, I am able to specify additional transverse web stiffeners for shear strength design checks, which will not be included in the finite element mesh, but will be included in the design calculations. The spacing between stiffeners is, of course, a critical parameter in the shear strength of the section. In this form, you specify how many checks you want on each girder. There is also this advanced button where you can specify either 1 or 2 layers of longitudinal deck reinforcement. This is specified via a reinforcement ratio and via a position of the rebar, the center line of the rebar so the distance from the center line of the rebar to the top face of the deck. And then you can, of course, you need to specify a concrete strength. And finally, you specify the location of these checks and whether this is positive bending, a negative bending, or a shear check. Very important, as mentioned, you need to specify which models will be used for the design checks. So you need a model for DC1S, a model for DC1C, another one for DC2, DW, LL plus IM. And this final one, LL plus IM, M negative, really means this additional model for the dual truck, which is required for negative bending. Here are the results. I have no checks on the first 3 girders, the first 3 tabs, but for the final girder, the exterior girder, here are the checks, as mentioned in the presentation. I can click the button, which will automatically open these design spreadsheets. The cells in gray are the parameters really obtained from the model, and in purple you will have kind of the intermediate or final results. So you will have, first of all, the composite section properties and positive bending. We're looking at the moments and lateral bending stresses, and then we get the factor stresses, the design stresses, and finally the design checks. Okay, so the compression flange for the tension flange and the limitation on the lateral bending. We have a similar spreadsheet for negative bending, where we first compute the composite section properties with or without the longitudinal steel reinforcement. We obtain the factored stresses, and then we look at the different strength design checks. So here, very importantly, the embraced length is calculated automatically by the program. And here are their final results. You can have the same finally for shear, the factored shear and the shear strength. And in this case, we're looking at an end panel, so this value would control. Of course, you will need influence surfaces for all that. So this will be, for example, the influence surface for different limit states here. This is extremely important for you to consider in your design. In this case, we're going to look in particular at negative bending at the pier. So we need to select the right influence surface, which is this one. And you can see this is the dual truck, which is positioned on each of the 2 lanes. Thank you very much.